Okay, so let's look at an example. Let the set X together with relation less than be a simply ordered set. Then the collection script S consisting of open rays of the form negative infinity to b and a to positive infinity, where a and b are elements in the set X, is a subbasis for the order topology on the set X. So proof: let the collection script B be the standard basis for the order topology on the set X. Then, for every open interval from A to B in the standard basis, this open interval is the intersection of the open ray from negative infinity to B with the open ray from A to positive infinity. Now, if B sub naught is the greatest element of the set X, then the open ray from A to positive infinity is the half open interval from A to B sub naught. And similarly, if A sub naught is the least element of the set X, then the open ray from negative infinity to B is the half open interval from A sub naught to B. That is, every element in the standard basis is a finite intersection of elements in the collection script S, and hence the collection script S is a subbasis for the order topology on the set X. Okay, so new definition. Let X be a set, and let the collection script S, which is the collection of sets S sub I for I in some indexing set I, be a collection of subsets of the set X such that X is the union of the elements in the collection script S. That is, the collection script S is a cover for the set X. Then the topology generated by the collection script S is the collection tau consisting of unions of finite intersections of elements in the collection script S. So we will prove that this is a topology. So let script B be the collection of all finite intersections of the elements in the collection script S. Then, as the entire set is the union of those elements, there exists at least one index I such that a given point x is in this element, and hence there exists at least one element in the collection script B such that the same point is in this element. Now let B sub 1 and B sub 2 be two elements in the collection script B. Then B sub 1 is a finite intersection of elements in the collection script S, and B sub 2 is also a finite intersection of elements in the collection script S. And so the intersection of B sub 1 with B sub 2 is also a finite intersection of elements in the collection script S, and hence the intersection of B sub 1 with B sub 2 is an element in the collection script B. So if a point x is in B sub 1 and is also in B sub 2, then there exists an element which we'll call B sub 3 in the collection script B such that the point is in this element, which is a subset of the intersection of B sub 1 and B sub 2. And thus the collection script B satisfies the conditions for a topology generated by a basis now every open set in the topology generated by the collection script B is a union, possibly empty union, of elements in the collection script B, and this is precisely the topology generated by the collection script S. So we can think of a subbasis as generating a basis in the sense that each basis element is a finite intersection of elements in the subbasis. So next we'll prove a corollary of the theorem dealing with a basis for a subspace. So let Y be a subspace of a given space X, and let the collection script S be a subbasis for the topology on X. Then the collection script S sub Y, consisting of the intersections of the set Y with elements S, where those elements are in the subbasis for the topology on X, is a subbasis for the subspace topology on the set Y. So proof: as the collection script S is a subbasis for the topology on X, the collection script B, consisting of finite intersections in the subbasis, is a basis for the topology on X. And so the collection script B sub Y, which is the set containing the intersections of Y with the elements B, where B is in the basis, is a basis for the subspace topology on the set Y. Now this collection script B sub Y is the intersection of the set Y with finite intersections of elements in the subbasis for the topology on X. Now, since the intersection of the set Y with the finite intersection of the elements in the collection script S is the same as the finite intersection of the intersections of Y with those elements, we have that the collection script B sub Y is the collection of finite intersections of the intersection of the set Y with the elements S sub J, where this intersection, Y intersected with S sub J, is in the collection script S sub Y, and hence the collection script S sub Y is a subbasis for the subspace topology on the set Y. Okay, so let's look at another example. Let X together with the relation less than be a simply ordered set with the order topology and let the subset Y of X be convex in X. Then for every open ray of the form a to positive infinity in the space X, we have that y intersected with this open ray is the set of all those elements x in the space X such that x is in the set y and x is greater than a. Now if a is in the set y, then this intersection, the intersection of y with the open ray from a to positive infinity, is itself an open ray in the space y, rather the simply ordered set y with the relation less than. Now if the point A is not in the set y, then A is either a lower bound of the set y or an upper bound of the set y, since otherwise there exists elements b and c in the set y such that the open interval from b to c is not contained in y, and this contradicts the fact that y is convex in the space X. So if A is a lower bound of y, then the intersection of y with the open ray from A to positive infinity is the set y, and if A is an upper bound of y, then the intersection of y with the open ray from A to positive infinity is the empty set. Similarly, for every open ray of the form negative infinity to b in the space X, the intersection of y with this open ray is exactly one of the following. An open ray in the simply ordered set y, the entire set y, or the empty set. So as an exercise, let X together with the relation less than be a simply ordered set. With the order topology, and let the subset Y of X be convex in X, show that the order topology on Y is the same as the topology. Y inherits as a subspace. Of the space X. Okay, so we'll end here for today. Next time, we will look at which topological properties are inherited by a subspace. So I hope you have enjoyed the 15th lecture. Thanks for watching.